6:30. All right. Timothy. Okay, first step, I'm going to go through this, your test today. Okay, what are the few things? I think some of you forgotten quite a number of things along the way after the holiday. So it seems like I'll have to do a quick recap on this particular area. So what we are going to do is I'll just go through this so that you will be able to make the correction. Let me see. So this one. So let's look at this. I think there are certain terms that you also need to be aware of. First one, I think most of you should be able to do it. Yeah. Okay, first one, the answer is B. Right. So I think all of you get correct because it's just a description. So which of the following show the correct number of lone pair? I think some of you didn't look at what is the number of lone pair. If you look at the number of lone pair, because your nitrogen will be combining with 3Cl. So in this case, it will be sharing one electron each. Then you have this one electron, you will have this power. And then you have a one electrons and then this. So if we are looking at the number of lone pair that is for nitrogen, you will have a one lone pair here. And then we also have a chlorine, you will have, because you have a 7, so you will have a 3 lone pair here. We also have a, yes, come in, we will have a 3 lone pair here. And then we will have a 3 lone pair here. Yes. So you're going to have a 10 lone pairs. Okay. A number of you who make mistakes, you missed out this lone pairs. What is generally the number of lone pairs? Okay, as H, it as poor conductor of electricity in solid states as the molecule. This one, I think most of you are okay. Do not have any free moving charge particle. Okay, which of the following is the correct VSER DPR geometry, which is basically the shapes. They are looking for the shapes. So if I'm going to look at CHCl3, or rather CCl3H, whatever it is, C is attached with 4 different substances. If it is 4 different elements, or not 4 atoms, the center atom C is with this. Generally, it will be tetrahedral. I think most of you actually look at triangular pyramidal. Triangular pyramidal is this one where you have ammonia like this. That is triangular pyramidal. Okay, so this is tetrahedral structure. Which of the following interaction is considered the strongest? I think you missed out the part interaction. So it is not necessarily intermolecular force. It can be anything, any interaction, any forces between them. So if you are talking about in terms of the strongest in nature, no matter how strong all these intermolecular forces, they will still be weaker than covalent bond. Because covalent bond, if you look at like those structure like diamond, as you can see, the covalent bond between diamond is much more stronger than any of the bond, whether it's a dispersion force or dipole attraction or even hydrogen bond. Because hydrogen bond, their melting point and boiling point is at most 100, as you can see when water, which is a hydrogen bond. If maybe it's in another things like HF, it may be slightly higher. But covalent bond can make it to have a, because this one is like something like the one that is done. So whenever you see that in terms of the strength, the covalent bond can create something which is like a diamond, that means it will be the strongest. So answer will be this one, not any one of them. I think most of you actually selected hydrogen bond. Yes, in terms of the based on this, the other three, hydrogen bond is strongest, but not as strong as covalent bond. Okay, so that is something that you need to take note. Describe the bond molarity. Okay, CO2 is normally non-polar. Yeah, it contains polar bond and a polar molecule. Which of the following correctly describe the bond in molecular polarity or carbon dioxide? Carbon dioxide is polar bond, but it is a non-polar molecule. I think it should be, yeah, right, B. Because carbon dioxide is polar, the reason of saying polar is oxygen is more electronegative than carbon. So in this case, this is going to be a D minus. So that means in terms of the bonds, they are polar bonds. But not all the polar bonds are always polar, will create a polar molecule because their dipole moments cancel each other. As you can see that one side and the other side, they are linear structure. Okay, so linear structure, it doesn't create polar molecule, it will just be a non-polar molecule. So that's why it must be this. Be careful about this, okay? Like water, it is a polar molecule, polar bond, but polar molecule. But carbon dioxide has a polar bond because always when you have a two different elements with different polarity or different electronegativity, then they will form a polar bond. This one itself is a polar bond, but once you have as I mentioned, when you have a two joined together, it becomes non-polar molecule because they cancel each other. Right? So that's something that you need to take note. The next one, which of the following correctly lists all the intermolecular force presents in the given molecule? Dispersion, dipole. Do we have a dipole? No, right? Hydrogen bonds. H2S is a dipole, and then CH4 is the dispersions and hydrogen bond. So which one do you think it is possible? Here do not have a hydrogen bond, so this is wrong. And you do not have a dispersion force, so lacking dispersion force will be resolved. Not correct. We do not have a dipole attraction here. So the only thing that is going to be correct is the dipole. It's a dipole because it is just going to be between H and S. You're going to have shapes. It's like the same thing like an H2O. H2S is the same as H2. Like this. Okay, so it will form something like this. Question 8, which of the following correct list the following molecule in order of decreasing melting point? I think some of you actually interpreted wrongly. Yeah, should be. So decreasing melting point, obviously H2 should be the decreasing. So it should be the smallest. Then if we look at this in terms of the bond, if you look at this, you will have okay, NH3, HCl, HF, these are the four things. So which one? Definitely this is the lowest and HF is the highest. So they give you all these things correct. So what you have to do is you have to look at this. The only thing that is different is here. Okay, since it is decreasing, cannot be C or D because this side is like greater than, so that means this is not possible. So we have to compare this NH3 and HCl. NH3 and HCl, which one is a polar molecule? Both of them are polar molecule. And but this guy has a hydrogen bonding. This one has a hydrogen. And this one is just a dipole. And hydrogen bonding is greater than dipole, so it should be. Okay. All allotropes is a same molecular compound but different chemical structure. Okay. And different structure formed from the same chemical element. Okay. Allotropes is for element. And this one, same molecular formula, different structure. This is called isomer. You will learn it later in organic compounds when we look at this isomers. So for allotropes, it's used for elements, so it must be B. Question 10. Question 10, most of you get correct. So diamond is the reverse of the dental drills, blah, blah, blah. Okay, Lewis structure. Lewis structures, normally what is inside the Lewis structure? Lewis structure must contain the bond as well as the lone pair, right? So in this case, oxygen, you need to put in the correct number of lone pair. If you don't have a correct number of lone pair, then you will not get the answer. You will get the mark. Each of them is one. And then here they are looking about the shapes. So what is this shape called? This shape is called what? Bent, yes. So it's asking for the name. Band structure. Carbon monoxide. Okay, remember we have tried to do carbon dioxide. Carbon dioxide is something like this. This is carbon dioxide because each carbon they require 4 bonds, right? But here carbon monoxide. Monoxide means, so that means we need to find what is the number of bonds that is going to appear between C and O. Okay. Oxygen has you can form because carbon normally what is going to have, carbon has a 4 bonds. So what is going to happen? This one, one thing what we call it in carbon monoxide, even like if you do not get that one correctly, most of you do not get it correct. So what will happen is that carbon monoxide is going to have a triple bond here. Okay, one of the triple bond, and what happened is so each of the bond, for each of the bond, this in this case is oxygen has this, and then carbon will actually be able to share. Okay, and then no, then what will happen is that carbon will have a one oxygen will have what we call a dative bond, but you haven't learned about dative bond. Then you will have 2 pairs and then this. But anyway, what I'm trying to ask you is for you to be able to grab into this. All right, so that is normally what we call it a carbon monoxide. This is going to be a linear. Ammonia is obviously we have this and with 2 lone, 1 lone pair with H. This one you should not miss. And this is called trigonal pyramidal. Okay, just give me a second. Please copy this first. Okay, the next one, draw the Lewis structure for the boron trifluoride molecule, BF3. This one we have tried it before. We have drawn that one before. Boron is in group 13. Okay, group 13. So which means that you are going to have a 3 electrons in its outermost shell. So it will be sharing with fluorine. So when they share, after it shares, since boron already shared, then you will form 3 bonds without having any additional, any lone pair left. So when you don't have any lone pair, generally what is going to be a dipole? Because this is going to be a minus, this is going to be a plus. So it will be something, because this dipoles will go from plus to minus, like this, plus to minus, like this. So you have it's like a planar structure with all these things going this way. Well, you have a polarity. We have a polar bonds? These are polar bonds. But can it form polar molecule? No, this is not polar because they cancel each other. Okay, so this is, we have to just write down non-polar or non-polarity, whatever it is. It's fine. I still give the marks for that non-polarity. So it's a non-polar molecule because their dipoles cancel each other. It's something similar to like carbon dioxide. When you have a linear structure, boron, remember you need to understand what is the nature of boron and try. They already give you this, and it's also give you the information that there are 3F attached to B. But you need to check in the periodic table which group is it in. It's in group 13. So it will have only 3 electrons in the outermost shell. So you can only share 3 electrons each. Of course, it doesn't fulfill the octet rule for boron, but it still fulfill the octet rule for fluorine. However, what happened is that when it's running out of electrons to share, this will still be just remain as it is. So what will happen is that this will definitely be non-polar because they will cancel each other. Any shape which is balanced like linear or like the plane structure, they will always cancel each other. Be careful about this, right? Okay, next one, they say use a knowledge of intermolecular forces. So they ask you to use the intermolecular forces to explain the difference in melting point for the following oxygen containing covalent molecule. Okay, so this is oxygen and ozone. Oxygen and ozone, which one has a higher boiling point? Melting point. Is it melting point? They give you a boiling point, yes. So which one has a higher boiling point? Ozone has a higher boiling point, okay? Yeah. Why do you think it's ozone has a higher boiling? This one has a higher boiling. So first of all, look at this too. We do not have a hydrogen bond in because there is no hydrogen. So in terms of intermolecular forces, we have to discuss based on 2 of them. One is the dispersion force, the other one is the dipole-dipole attraction. So there's the oxygen has a, okay, when in any covalent compound, you will have a dispersion force. So which one has a larger dispersion force first of all? Ozone or oxygen? Obviously ozone because there are more electrons, right? So ozone O3 contains higher number of. Remember, whenever you want to discuss dispersion force, you need to base on the number of electrons. So O3 contains higher number of electrons. So it has higher dispersion force compared to oxygen. So that's the first step. Then you must also mention that that's one point. The second point that we are going to look at is on the polarity. If you look at in terms of the shape, O2 is non-polar, but O3 is polar due to its band shape. While O2 is non-polar. So overall, what can you say? Overall, they give you 3 marks. So that is for 1 mark each. So the next one is going to be so overall intermolecular force between O3 is higher. So you will need more energy. Generally, even if you can write down like this, you can get 3 marks. Okay, 3 key points. Maybe just say more energy is required to break them apart or move them apart. More energy is required. Break them apart. For your information, when you are answering in science, you do not need to repeat any given informations, like unless they ask for the analysis from the table. But that is not for your level. Your levels just require for you to just go down to the point. Don't waste your time like trying to explain a given fact. Like, oh yeah, ozone has a higher melting boiling point than this. No need to write them down. Break them apart. They will look for the key information so that it's for 3 marks, 3 points, right? Are you done? Yeah.
Why is that if it's polar?
Which one? Ozone is why is it polar? Because of this band shape.
Like,
No, this is polar.
They're not
Okay. Because it's and in terms of the number of molecules, they have a different a different number of lone pairs. It will actually make it because of the different number of lone pair, it will become polar and
polar.
polar and polarity. It's not just
But it's
in terms of the nature is non-polar, yeah, because it's the same. They do not have polar bonds, but overall molecule it is. So the shapes and then the distribution of the lone pair electrons. Okay, next one. Draw the diagrams of the covalent structure of a property of carbon electrodes. So which is about diamond and generally graphites. So for diamond, you need to draw like something like at least you must represent with a dot, then you will have a dot bond. So each of them will have a 4 of them like this. Then you will have something like this. Then you will also have something like this. Also have something like this. At least if you are able to draw and probably draw it this way. So you can just you need to at least say that the dots represent a carbon atom. So this one carbon atom. At least you need to mention. Okay, so if you do not write anything, then we don't know what are those dots here. So you need to mention that these are carbon atoms. Okay, and we have so what we are looking at is for each carbon atom, there are 4 different bonds joined together. Okay, then for the what we call it graphites, then you are going to have hexagon shapes. So maybe I need you to at least draw like 3 or 4 hexagon shapes, maybe 4 of them. And that each of them will have a carbon atoms here. So again, these are carbon. At each the junction, then you must have each carbon atom. So these are your. So that will give you 2 marks each, the shape and then the position of the correct carbon atom. Then explain why diamond is considered to have a greater hardness than graphite. Normally you can try to use diamond has a tetrahedral structure, and then they so 4 marks. Generally, what we have to do is we have to compare this with diamond as tetrahedral. In which each carbon atoms, each carbon atom is connected to other 4 carbon atoms in a very rigid structure. With strong so that give you the key informations that in terms of the marks that we are looking at is the tetrahedral structure, and then it's a rigid structure with a strong covalent bond. That will make it diamond to be very hard. But the question is that you need to compare that with the structure of graphite. But for graphite, each carbon atom one with three other forming layers of plain hexagonal shape. And pauses between them, the planes, weak. Expression force. Okay, so that this one generally tells you that since it is weak, then it is a weak structure. This is a hard structure. All right. So yeah, the way, as a general comment, you need to be able to approach the theoretical questions with the key information. We are not looking at the impressive way of writing. We are just looking at the key, right? You need to be able to catch those key information. Is that fine? Any question? If not, then I'm going over to the. I'm going to continue with today's lessons. Part one. Do we still have anything left in the part one? Let's see. This is where we stop. Yeah. Okay. We haven't started the structural properties. I thought we have done with this. So let's continue with this structural property. Oh yeah, last week we were doing. Oh, we were doing those exercises from the previous one. Okay. This is what we are going to continue. Structures and property for ionic compound. Remember, we have started looking at the ionic compound. Ionic compounds generally have a give and take. Okay, they form the bond by giving and taking of electrons by forming positive ions and negative ions. So this is an ionic compound bonding model where we have a, this one is generally metallic, this is metal structure. So when you are drawing for metal, then you should be able to draw this one. This is the metallic lattice structure. It is on the right side. This is the metallic lattice structure. And then ionic lattice structure for ionic compound is this. So you should be able to draw alternate positive and negative ions. There is no delocalized electron. Okay, here we have a delocalized electron. The bonding is formed between these delocalized electrons and positively charged metal ion. Combined together, that gives you the metallic structure on the left side. Okay, but for the ionic lattice structure, we need to be able to draw this. So for the ionic bonding model, then it must be a three-dimensional crystallitic structure. Okay, then the one thing you need to take note about these terms, ions are also held and in a fixed position in the organized arrangement. So sometimes they use regular arrangement. Okay, They can either use either a regular arrangement or organized arrangement. This one composed of this, but there is no free electrons. So they are in the solid crystal structure, they are fixed ion. So having this fixed ion make them not to be able to conduct electricity. Okay. They can conduct electricity because their ions are not moving. Okay. So like in the metallic bonding model, there is a strong electrostatic force of attraction between. So that is a strong electrostatic force of attraction between the positive and negative charges. But the attraction is between the cation. That is the difference between these two models. Okay? This attraction is between the cation and in the lattice. No free moving electrons, completely donated. So the force of attraction between the cation and anion is referred to as the ionic bond. So it's just a way of representing ionic bond. It's like a very strong electrostatic force of attraction, so that they will be still in their place. And for them to break them apart, you will also require large amount of energy. So they will have these following properties. Okay, so what are the following properties? Properties of ionic compounds: high melting and boiling point. So why do they have high melting and boiling point? This particular topics are very important. They will always ask you theoretical questions. As I can see that you have a weakness in understanding and writing, or rather writing. It's not understanding. Writing, if you are weak in writing, make sure that you are able to remember those key points here. Okay, they may ask you why ionic compounds have a high melting point or boiling point. Then you make use of these paragraphs to answer. So what should be included in that answer? So obviously, one key that we are going to reuse again is called bond strength. So bond strength is between two bonded atoms is a measure of energy required to break apart one mole of, okay, even though like when they say covalently bonded molecule in gaseous state, okay, even though they say covalently bonded molecule, it just in terms of the definition that we have, but here in this case in ionic compound, we can also consider them in that manner. Okay, so that is the bond strength. So the bond strength of double bond will be stronger than single bond, obviously, and then triple bond will be stronger than the double bond. Sorry, triple bond, yeah, will be stronger than the double bond. But this is used for covalently bonded molecule. But for the ionic compound, we use an intermolecular force. Attraction between the cation and anion. So when heat or thermal energy is applied to a solid ionic, this causes the ion within the lattice to gain energy and they will start to begin to vibrate. Then this ion then transfer the energy to other ion, eventually causing nerve disruptions when the ions are able to move. That is what we call it melting. So if the vibrational force, which is your kinetic energy, is more than the energy that is binding them, which now sometimes they call it electrostatic binding energy. If the energy that you are given to each and every ions is more than their binding energy, then they will start to break away from their position. So that makes them to start to melt. Okay. So that's the nature that is going to happen. Here, key point is that you have a negative and positive all in line structure. Can you see they are aligned? Okay, they are regular pattern. Okay, alternate regular pattern. But when you give a heat, they get disrupted. But normally when the lattice gets disrupted, they are able to repel because, okay, currently you have a positive and negative alternate. But what will happen if I'm going to shift this to the right just by one layer? then what will happen is the negative will be next to the negative. Positive will be next to the net positive. Then they will start to repel each other. So once they repel each other, then it's easier for them to lose their regular pattern and structure. Okay, so this will also be used in another way. So, right, what are the factors that affect the melting and boiling point of ionic compounds? One of it is the size of ions. The bigger ions, more spread out, the charge are, which leads to a lesser electrostatic force of attraction. So, if you are looking at two ionic compound, one have a smaller ionic compound, smaller molecule, smaller atoms. The other one is a bigger atom. Bigger atom will have a lower melting point than the smaller one because bigger ion is going to be a lower boiling point or melting. Charge of ion. Okay, even like if you look at this, for example, like if I'm going to compare NaCl with MgO. Okay, and NaCl is formed between Na plus and Cl minus. But MgO is formed between Mg2 plus and O2. Which one do you think will have a higher melting point? Yeah, magnesium oxide will have a higher melting point, obviously. Okay, because first of all, oxygen has a smaller molecular size, a smaller atomic size, so they have a smaller size of ions. And then they also have a greater number of charge because it's a now it's between 2 plus and 2 minus. Here is plus and minus only. Okay, so you must take note of this. So this greater number of charge of the ion, the greater electrostatic force of attraction, this will be a higher boiling point and not. Okay, example 4b1. Think about it. Lithium fluoride and lithium fluoride and sodium fluoride. Sorry. Yeah, lithium fluoride and sodium fluoride. Which one do you think will have a larger force of attractions between them? Anyone is able to give me? Daniel? Which one do you think is going to have a larger force of attractions? Lithium and sodium, which one is a smaller molecule? Obviously, sodium is below lithium. Definitely, sodium is a larger molecule, larger atoms, one more shell, right? But the fluorine side, same size. In terms of charge, fluorine is also minus. So the lithium is plus. Sodium is also plus and minus. So they have the same charge, but it's lithium has a smaller atomic size, right? So smaller atomic size mean higher melting point is the lithium fluoride. Okay, so you can mention here's that for both compounds have the same of them have same charges on their ion. You can just write down like +1 and -2. However, Now, if they have the same charge, what we have to compare? We have to compare the size of ions, right? However, we can say that Li plus is smaller than Na plus. So LIF has stronger electrostatic attraction. Between ions, between its so LIF has higher melting. So when you answer, normally they will give you 2 marks for this. Okay, I know it's a little bit long, but what are the key points that I'll be looking for, or rather the examiner will be looking for? Okay, if they give you 3 marks, you need to mention that they have the same charges on the ions. This is something like a little bit of extra here. So this is normally going to be a 1 mark, but you need to mention about this and then stronger electric force of attraction. So these are the marks that we are looking, the key points that we are looking for. Even like if you say do not have a conclusion that even if you do not make a conclusion that LIF is a higher melting point, yeah, but here in this case it's already it's like yeah, it's best to put in that way. Okay, CaF2 determine whether CaF2 or Ka will have a higher boiling point. Compare their structure. Okay, please answer it. Which one? CaF2 or KF2? KF, sorry. F and F, so it's same. What is different? The one difference is the potassium and calcium. Because actually have equal difference. Yeah. What do you think? First of all, look at the charge. What is the charge on the Ca? 2 plus, right? Group 2. This is plus. So you have a minus, of course, you have a something like 2 minus and sorry, one minus here. So this is going to be a 2 minus overall, and then this is going to be minus. So obviously calcium fluoride will have a larger, higher boiling point. This one will have a higher boiling point. So how do we answer? We can say that both Ca and K are in the same period. So they have a their ionic size or ions size are similar. Okay, their ion size are similar. So we need to mention, you need to mention that ion size are similar first. But Ca2 plus has higher charge than so definitely this one will have a higher melting, right? That one. You have to think here because of the charge. Because K plus K has only plus, right? Ca has 2. C is in group 2, right? Group 2, then when they form the ion, remember in part A, we try to form ions. Ca will form Ca2 plus, right? Yeah. So because of it's generally what we can say is that the attractive force between one plus and one minus, and two plus and two minus, two plus and two minus will be stronger than one plus and one minus. Because of generally what we can say is this two plus has a higher nuclear charge, right? So you can also say that the electrostatic force of attraction, you can put in something here. Electrostatic force of attraction between Ca2 plus and N minus ions are higher. So if you can include this statement, that will be better. They are looking for the higher electrostatic force of attraction. That's what they are looking for. Okay, I'll give you about 2 minutes, 3 minutes. Think about this. Question 1. Okay. Which one do you think has a higher melting point? Aluminium nitride. Okay, this is phosphide and nitride. This one is from nitrogen. This is nitride. Okay, why is it? Yeah, smaller. So this is 3 plus and 3 minus. This is also 3 plus and 3 minus. So you need to mention that phosphorus and nitrogen, they are in the same group. Okay, so both P and N are in the same group 15. But what about ionic size? Which one has a smaller? N 3 minus S smaller ionic smaller ions or forms smaller ion, whatever it is. So again, you must mention electrostatic force of attraction. Electrostatic force of attraction between Al3 plus in N3 minus ions are strong. Then this one will have a higher energy. So this one is comparing for the melting point. Of course, it's also for the boiling point, but it will be more obvious for melting point because you start to break away from the solid structures to become a liquid structure. Okay. You need to compare based on the two factor. One is the size of the ion, the other one is the charge. Your answer must always refer to either one of them. Sometimes it will be varying both. Sometimes it will be varying only one. And then the other one is the same. Here in this case, charge is the same, but size are different. Okay. It doesn't really matter. You can't, okay, the question is that then you will be asking, okay, one is smaller, one is bigger. They won't ask you like that. This one will require another understanding the total, what we call it nuclear charge. But in your level, they won't be varying both. When they vary, they will only vary one. Okay, so these are the typical questions. Sure. The other one is hardness and brittleness. They are generally very hard because of their attractive force. Due to their strong electrostatic force of attractions between their cations and anions. But when you shift this ion lattice, attraction needs to be overcome. If you want to try like sort of like inform it. But if enough force is applied, then these layers of alternating cation and ion do shift. This results in like charge lining up, and ion with anion cation causes the light charge to repel each other, and then the crystallic structure will shatter. So normally, most of the ionic compounds are brittle. Okay, if you look at like salt. So when you try to buy a salt which is like a large crystal table salt, you try to hammer it, then they will change it into powder easily. So it doesn't sort of like some compounds where they deform, they do not have a deformation, they will just break. Okay, so that's the reason why again I've explained here. What happens is that when you give a stress, if in the ionic level that deformation is quite big, but for us it's like you find it doesn't even change the shape, and how come it's brittle like a shelter? Because of these reasons. Okay, so when they line up, they will actually repel each other. Repulsion force will make them to break them apart. So key points. The one that I have underlined, if they ask why are they brittle, then you should be able to explain. But this property is different to that of the metal, which are malleable and ductile, opposed to being brittle. Because metallic bonding consists of only cations in an organized crystalline surrounded by sea or negative delocalized solution. So when the force is applied, the cation move, but this delocalized electrons floating between these ions can also move, and the electrostatic force of attraction is maintained. So that's if they ask you why metals are malleable and ductile, while they have electrostatic force of attraction between cation and electron, but for the ionic compound, they are brittle. So these are two contrasting models that you need to be able to understand. So this is for ionic, and this is for metallic. Not only the point that you should be able to explain why ionic compounds are brittle, you must also be able to explain why metals are malleable in dark times. Because normally they can combine the informations together for you to be able to find or like give a contrasting structure. Yeah. No, metals are not ionic. Metals are just metallic structure. Pure metals just have a metallic bond. They do not have ionic. No, but it is an electrostatic force of attraction. Remember, we have previously we have this metallic structure here. Remember this now?
Yeah.
Yeah. So it's between this page. This is metallic. So when you try to deform, these electrons also move together. So they do not actually repel each other. There are electrons which are in between them. That's why they do not break away from each other. Okay. They are also possible that, okay, but what will happen when there's some of the metal, if you put in like other atoms, make them to become like alloy. So when you make them alloy, those alloy will make them more brittle. For example, like steel. We have a cast iron and then mild steel and cast iron. Cast iron is very brittle, but it's much stronger. Okay, but you can't actually sort of like bend it but very hard to bend as well. But once it's bent, it also is more likely to be broken. But like mild steel is a bit more softer, but it's more flexible. Okay, so but that one we won't be looking at very much details about this. But generally, what happened is that based on the structure of metal, when those cation moves, the electrons also move together, so they do not exhibit brittleness in metal. So they can ask you why metals brittleness is not exhibited while ionic compounds show brittleness. Then you should be able to explain based on this statement. All right? Because this one doesn't have electrons which is going to be moving on in between. They are like sort of like fixed structure of ions. So once they move, they will repel each other. All right, so but this is a model for the delocalized. As you can see, even like this is shift. As you can see, these electrons actually move together with them. Okay, so that is the difference between them. Electrical conductivity, that one is quite obvious. For ionic compounds, we have ions, but those ions in solid, they are not able to move. So in solid state, they are fixed position. Ions and anions and ionic compounds and fixed positions in the lattice structure, not free to move. So they cannot conduct electricity in as a solid. Molten and aqueous state, but in a molten state, which is melted, a molten state normally is represented as a liquid. Aqueous is like solution state. We will talk about the solution in the next lessons in a 4C. Okay, as a result of heating, disrupt the electrostatic and then cause them to. So ions become freely moving and they can conduct electricity because for the ions, for the electricity conductivity, you need them to be able to carry charge or able to move. Okay. This particular knowledge will be useful later on in Unit 3 when we look at galvanic and electrolytic cells. In another way, ionic compounds can conduct electricity as if they are in electricity. I don't think this one is here. I think just can conduct electricity if they are in an aqueous state. In other words, dissolved in water. Water is a polar band shaped molecule. Because of that, we'll discuss about this in 4C in more details. Okay. So one side of non-symmetrical molecule has a partially positive charge. So it can form like a hydrogen atoms. The other side is it's just a recall of a hydrogen bonding. So, but the important thing is this partial negative charge will attract to this. So this draw the outer ion. It's just a detailed explanation, but what actually happened is here. This is what happened. Key points is that the electrostatic force of attraction between the cation ion is replaced by the ion dipole attraction between the ions and water molecule. But it will not always occur. So what I'm trying to say is not all the ionic compounds are soluble. We will talk about that solubility in the next chapter as well. I mean, next section and next chapter. Okay, there will be a continuation from there. So that this is what happened. What happened is the water molecule will go in between them, replacing them with the electrostatic force of attractions by replace, because water molecule is able to provide both positive and negative charges. Okay? But whether it's able to be soluble, what are the factors that affect the solubility? We'll talk about this more detailed in the next chapter. I think this particular question explain the difference between electrical conductive ionic compound in solid and molten liquid state. So you have to say that in solid state, ions are in fixed position. In solid state, ions will be able to move and therefore electrical conductivity in liquid state as ions are bound what is the difference? These things I think you should be able to just explain them. I'll leave it up to you for this section 4B, some of the questions. I'm not going to do some of them. 1, 2, I'm going to skip. Similar to some of the limitations that were presented for the metallic bonding in chapter 3, identify some potential limitations of ionic bonding model. Okay. What are the ionic bonding models? So if you are going to describe the ionic bonding model, what are we going to be doing? What are we going to be mentioning about those things there? Ionic bonding model. How do you actually explain ionic bonding model? Yeah, it's a lattice structure, and also they are formed by the generally what do you call it, donating and accepting of electrons. And how do they actually arrange? Donating those valence electrons and gaining them, and we have a positive and negative charge So those resulting those then things between the positive and negative charge, negatively charged ion. So we need to say that transferring, we need to mentioning transferring. Transfer is generally we need to either say donate and accept electrons, valence electrons. Forming oppositely charged so bond is formed due to the bonds to the electrostatic force of attraction. Due to the electrostatic force of attraction between okay, so this is basically your ionic bonding model. So in the ionic bonding model, what are the possible limitations? This particular bonding model just only tells you that they will be in they will form like electrostatic force of attraction, but they do not mention anything about three-dimensional regular arrangement. Okay. So that means this particular model does not inform or like explain how those ions are arranged. Arrangement of them is not in three-dimensional space. It also does not explain the different melting point and boiling point of different ionic compound. Because if they say that if they have electrostatic force of attraction, they should have a similar melting point and boiling point. But that particular model does not explain why different ionic compound has a different melting point and boiling point as well. The electrical conductivity of those compounds in different states. Okay, so there are generally three limitations. The model does not inform or explain the opposite, how these ions arrange in three dimension. Next one is it also couldn't explain when it moved on. Then one. So in addition, it cannot explain. Wow. Bonds. Different electrical conductivity. Difference. That's generally the weaknesses, or rather is the limitation. This one I will just leave it up to you. Yes, but this model, the model just tells you, ionic bonding model just tells you that there's an attractive force between them that bind them together. But they do not mention about those layer and regular arrangement in the model itself. The model, okay, this ionic bonding model say it forms when the transfer of electrons form oppositely charged. Okay, sorry, this one is oppositely charged. Oppositely charged. Oh my gosh, what is wrong? Charged ion. Okay, so it's oppositely charged ion bond are formed due to the electrostatic force of attraction. That's all. It stops there. Okay, but it doesn't mention anything about the three-dimensional shapes. It's not in the model. This one is by the further study, further experimentation. It's from the physical natures they actually study backwards. Ionic bonding model doesn't explain this directly. That's what you have to do.
It's not actually. This is just.
No. It is normally obtained. This too doesn't explain it. Just by looking at forming, giving and taking of electrons, forming cation and anion. So bonds is formed between the force of attraction between cation and anion. Doesn't say that they will have this particular structure. The arrangement is not explained. It could be in another way.
But it has to be.
Yeah, because we are studying backwards, sort of like a little bit of a backwards. Okay, Paul, I will leave it up to you. It's already in your notes. Use the ionic bonding model to explain the following properties of ionic compound. Potassium bromide melts over this high melting point and boiling point. So you need to make use of the high melting point and boiling point. You just have to just explain that due to their strong electrostatic force of attraction. Oppositely charged. So require large amount of energy. Hard and brittle, solids at the room temperature. Hard is due to a strong force, strong. For the brittle part, it's due to the because of the arrangement. It is the arrangement of this small movement cause them to align and same charge repulsion. So brittle because of that. Poor conductor of electricity, no over iron. Because ions are fixed in fixed position. Molten state, ions are able to move. Because it's normally when you apply like a potential difference that will make them to move. Okay, I'm just giving like a key structure. You can look at something. Okay, melting point of NGO is more 3.5 times greater than the melting point of this. So just reason why this might be the case. Mg is 2 plus, O is 2 minus. So both ions have larger or higher charge than Na plus and Cl minus. And both Mg2 plus and especially O 2 minus will not really exist. So that makes them to have a stronger electrostatic force of attraction. You always need to conclude with a stronger and weaker electrostatic force of attractions, okay? You can't just stop your explanation here. You still need to mention about that causes a stronger electrostatic force of attraction. Is there any more interesting questions? I think the next question we have actually tried to explain more or less similar because it's a potassium cation is larger than sodium. Yep. Both are equally important. Yeah, I mean, this extra charges also cause them to have a stronger electrostatic force of attraction. And then also like the ionic size are smaller, which is also a stronger. It also causes a stronger electrostatic force. The bigger one has a weaker electrostatic force. Yeah, they are equally the same. So both points are favoring this guy to have a higher, having a stronger electrostatic force of attraction. This one, same thing, NCl and KCl. NCl is smaller size, so charge is the same, and Na is smaller size, so that's why it has a higher melting. Explain why NABR is hard and brittle. Also the same thing. You can explain based on just now explanation. What about ionic compound dissolved in water? Why the aqueous solutions conduct electricity? So you need to explain that one, that water molecule will displace their electrostatic force of attraction. In the meantime, why are they able to conduct electricity? Because ions become mobile in the aqueous. Right? So try to do them as your homework. Next week, I can give you the notes first for the next week so that you can read them first. Okay. We are going to talk about precipitation reactions as well as the understanding of how we are going to look at the actual dissolving of water in the water. Yeah. Right. So I'll stop here. Yeah. It's very hard to compare like that. But generally, ionic bonds is normally stronger. Generally stronger. Yeah.